Hello and welcome to Try a Maths Problem today. First thing to get out of the way is the drawing. I know it's not to scale, so if that's why you're here, I hear you. What the question actually says is we have three triangles that are Pythagorean triangles. That means they're right angles and their sides are integers. So the first one is the famous one that you see there. It's with sides 3, 4 and hypotenuse 5. The next one we have there is a side 5, 12 and hypotenuse is 13. The last one we don't know. That's what we're looking for. I'm looking for all the sides to this last triangle. The extra bit of information we're given is the smallest angle in each of these triangles add up to 90 degrees. Now there is a trivial answer to this if you use a calculator, so I'd avoid doing that. There's actually a few answers. I'll give you my answer in the rest of this video. But I do recommend you pause first and try your own. Then see if I did the same one or if my solution agrees with yours. But either way, I hope you enjoy the rest of the video. Okay, here's how I thought of the question. First thing to note is the smallest angle has to be across from the smallest side. So we're dealing with, my drawing already conveyed that, I hope. So we're dealing with these two angles here, A and B. So my first thought was, the angles adding up to 90 degrees, that could be useful if we take the sine of them. Say sine of A plus B plus C. This is going to turn out to be a bit of a mistake anyway. Because the sine of all this would equal to 1. Sine of 90 is equal to 1. And I know a lot about sine of adding angles. We have a rule of adding two angles together. We can break that apart into sines and cosines. And this is just two angles. If you group two of them together first and then break them apart again. So I did this a little bit and then I realized, hang on, why am I using something that equals to 1 when I could use something that equals to 0? So I could see the writing was on the wall. It was going to get a little difficult. So I abandoned that idea and I used cosine. Cosine of A plus B plus C. That's cosine of 90. And that's equal to 0. So that's how I'm going to continue on with this question. To break this apart, I'm going to use a famous trig identity. I'll jot it up here. Cosine of A plus B, not the same A plus B, just generic angle plus angle is equal to cosine the first angle, cosine the second angle minus sine the first and sine the second. I have not memorized this. I've been learning or teaching maths for 40 years now. I always just look these up. As we continue the question on, we're also going to use the other one, the sine identity. So let me just jot that out first. That's equal to sine the first angle, cosine the second angle, plus cosine the first angle times sine the second angle. Again, I have not memorized these, just looked up. You can derive them, of course, as well. We're not going to do that in this video. So I'm going to use them to break this apart into multiple different levels. It'll get a bit boring, so I do recommend fast forward or even skip ahead in the video. So I'm going to break this into two angles. I'll just say A plus B and C as the two angles and follow the formula up here. So this formula will tell me that this is now equal to cosine the first angle, in this case that's A plus B, multiplied by cosine the second angle, in this case it's C, minus sine the first angle times sine the second angle. Now this is all equal to 0. Now hopefully you can see what my plan is here. I'm just going to break all of this apart. And to skip ahead, remember I actually know what, let's say, sine of A is equal to. I know it's equal to the opposite over the hypotenuse. So that's equal to 3 over 5. Let me write them all down while I'm here. Sine of B is equal to 5 over 15. Cosine of A is equal to 4 over 5. And cosine of B is equal to 12 over 15. So once I break all of these apart, what I'm hoping I have, and it will turn out that way, I'm only left with a sine C and a cosine C. Hopefully I'll be able to put them together in some way. Sine and cosine join to make tangent. And I'll get an answer from there. I'm skipping ahead though. Let's continue on with this breaking apart. Cosine of a plus b, it's all written up there, so certainly feel free to fast forward. And we have a cosine b minus sine a sine b. All of that is multiplied by cosine c. Take away, again, we're just writing down what I see here. Cosine b plus cosine a sine b, all that multiplied by sine c. And all this is equal to 0. I think you'll agree this is quite a mess, but remember we have lots of information here. We have cosine a, I know that's 4 over 5. Cosine b is 12 over 15. Multiply these together, we get 48 over 65, and so on with a lot of these. This one would be sine a by sine b, that'd be 15 over 65. These two here multiply, let's see, the a and the cosine b, that'd be 36 over 65 plus 20 over 65. So we could clean a lot of that up. I'll squeeze it in over here. This would become 33 over 65 times cosine c. That's all that becomes, minus, this is 56 over 65 sine c, and that equals 0. We can get one of these on their own. Let's get sine c on its own. Sine c will equal, move the sine c over, I guess, will equal cosine c. It has a 30, I haven't left enough room there, 33 times 65, and we'll end up multiplying by this 65 and dividing by this 56. 65's cancel. Divide both sides by cosine c. And we're left with sine c divided by cosine c is tangent of c, and that will equal 33 over 56. Now, how do I get from here to the answer? I didn't leave enough room. Let me squeeze in a triangle somewhere. If this is the final triangle, if we know the tangent of this c up here is equal to 33 over 56, we know the tangent's equal to the opposite over the hypotenuse, over the adjacent. So that's 33 is across here and 56 is up here. We'll go ahead and use Pythagorean theorem to find this length here. Now I've run out of room on the board, so I'll just go ahead and tell you from doing it myself that this is 65, and that's the answer to that question. Now if you want to stick around for another 5 or so minutes, I'll outline 2 other very different ways you could have done this question. The first of the 2 other methods I want to show you is one involving complex numbers, just because I rarely get to use complex numbers except when I'm just teaching complex numbers. In this case, we're going to use them because complex numbers are really good at when circles are involved. Now, of course, in this case, there isn't a circle involved. We have a triangle, a right angle triangle, but that can be put inside a circle and then turned into a complex number. So the first angle we're dealing with, we're interested in this angle in here. That'll become clear in a moment when you're using complex numbers. So the first triangle I'm going to use is the length 3, 4, 5. Just important you put 3 over here, so we're dealing with the correct angle. And this can be represented as a complex number. We call it omega 1, and that would be equal to the length 4 in the real part and length 3 in the imaginary part. That's 3i. You could also do this in polar form in different ways, but I can represent the first triangle that we were given by this complex number, where, as I said, now the argument of this will give you the angle in here. So that's going to be useful. And the second one that we're given could be represented as, let's see, across from that. So that's 12 plus 5i. Oh yeah, I'm only outlining this, so I'm not going to go too much into detail. And the last one, we'll leave that one blank, or we'll just put it in as a generic a plus bi. Now the interesting thing about complex numbers is when they're represented in polar, well this isn't in polar form, but the same idea applies. When you multiply complex numbers, really what we're doing is transforming a point, and we're adding their angles together. We're sort of multiplying their hypotenuse. We won't go into that in this case, but what's important is we're pretty much adding the angles together. So what you end up getting is a triangle, maybe plus another triangle. It doesn't have to have the same circle, of course, and then maybe plus another triangle if you multiply three numbers, which we are going to do here. Multiply all three of these together. We should get a final answer with a angle of 90 degrees, because remember we're adding each of the angles together. So if the last one, a plus bi, and what's interesting about 90 degrees, the answer in a complex form, something that has a 90 degree angle, I'll draw another circle so it doesn't get too messy, a point that maybe it ends up somewhere up here, the circle's not important by the way, maybe it ends up somewhere up here with a 90 degree angle. What's important about that is its real part is 0. So whatever the answer is, it's like ni, it's something with only an imaginary part. That means I can multiply all of this out, and I'm only interested in the real parts of it, and it should all equal to 0. And we're going to use that to solve the question. Let's just multiply these two complex numbers first. 4 by 12 is 48. 3 times 5 is 15. Turns into a minus 15. So we get 48 minus 15 is 33. We had that in the previous part. That's interesting. The real parts of this, 4 times 5 plus 3 times 12, that's 20 plus 36. We had that in the previous section as well. 56i multiplied by this other triangle as well will still equal 0 plus some number. I'm using n because I'm copying this from not fully copying it, but I got inspiration from looking at an answer to this question online. Multiplying these out, I'm only going to interest myself in the real part this time. We get a real part by 33 times a, and we get another real part by minus 56 times b, times I, 2 i's multiplied make a minus 1. So we're left with this, and we know this real part on the left has to equal the real part on the right. And remember what this is saying, this final triangle that we're interested in, the a part I've decided was the real, which would be not the longest. So b is the shortest, so b would be down here. Sorry, I've confused that by tilting this again. So the answer here is two numbers obey this rule here. So if I rearrange this, we'd get, say, b is equal to, let's see, 33 over 56a. Any two numbers that obey this will work. The only thing is we're looking for integers. And I never mentioned in the previous part, but there's infinite answers to this question. We just found the smallest one. In this case, the smallest answer you could get is, what if a was 1? Well, that wouldn't be an integer. A is 2, it wouldn't be an integer. So the smallest number for a you could get is 56, because that would make b an integer. So that'd be 56 here, 33 here, which is the same as we got in the previous method. Again, you use Pythagoras theorem and you get 65 here. I said I was only going to outline that. I think that's maybe a bit more than an outline. Next one I will just outline because I haven't done it out on a piece of paper. It just looks really cool, so I will show you it. The final method I'd like to show you, it just looks cool in a picture. So what the person did to solve it is they lined up all the triangles together to make the three angles that add up to 90 be a right angle. So they took, I'll just have a quick glance at my notes here. They took the 12 and 5 triangle, and that was length 15, 13. the hypotenuse here. And they lined up another one here. So here's like this angle was B in my picture, this one A here. And if they put C here, this will add up to 90 degrees. And we're going to use that fact. But also they wanted this to line up the whole length of this. But the first triangle we have is 3, 4 and 5. And they want it to be 12 long. So, and they also want the A angle to be in here. So they just multiplied it by 3. So instead of being 4 long, it was 12. Instead of being 3 over here, it was 9. Instead of the length being 5, it was 15. So they got these two triangles on top of each other, but still A and B in here. And the last one, again, we don't know its length yet, but we can just bring it up here and put its right angle over there. We have one of its sides is now 15. What do you do next? If you continue this line down and continue this line across, what they use the fact that, quite interestingly, this triangle from here, here and here, this big triangle is identical to this triangle down here. And that's because, let's see, these two, A plus C, must equal 90 minus B. So must this side in here. This must be 90 minus B. So they're the same. That's 90, that's 90. So this one in here must be B. And that means we have another triangle now. We have this triangle in here is B right angle and whatever this angle in here. I guess we can, now this is A plus C. This in here is A plus C. They're all equal. We have similar triangles everywhere. So, and we know one of this length. We know everything about this guy's length. So if I write this this triangle here again, we know that's 9. And in the original case, it would have been 5. So this triangle is 9/5 bigger than this one. So its hypotenuse is 13 multiplied by 9/5. Its length here down the bottom in this case is 12 multiplied by 9/5. So you're filling in lots of information in here. Similarly, no pun intended, but it's a good pun I suppose. This big triangle, as I already said, is similar once more. We know this length. We know this length. So this length is 12 plus whatever this mess is here. I haven't solved it out, so I don't have any neater numbers. This is similar to this one, or similar to this one, whichever you rather. So you should be able to get this whole length here. You can get this length. We already know this length. Take them away, you should be able to find this length. You now have this length and this length. You could do the same method here to find this one. You found all 3, or you could find 2 of them, use Pythagoras theorem. Once again, you wouldn't get 65 as the hypotenuse. You wouldn't get integers everywhere. 15 would be here. Everything else would be off by a certain amount. You'd just multiply them until they all became integers, and you should find the first time that happens is 65, 33, and I forget what we got previously. Anyway, that's my outline to it. I thought that was a really cool way to do it, but like I said, I didn't do all the numbers out, so apologies for that. This video has gone a bit long. I've outlined them a bit more than I planned. If you are still watching, thank you very much. I do hope to get 1, maybe even 2 of these videos out every week. So if you do like, subscribe, hopefully they'll come up on your feed and you'll see more of them. Thanks for watching and have a great day.